So today we're going to cover a couple topics. First, we're going to derive and explain why the vapor and liquid molar Gibbs energy of a component must be at equilibrium, and we're also going to derive the Clausius-Clapeyron equation. So for this first part here, I'm going to go ahead and draw out an example system. And up top here, we're going to have some gaseous phase. So we're going to have the Gibbs energy of the gaseous phase and the moles in the gaseous phase. I'm using V for vapor. And then we also have some liquid phase. Now, what can be said about this entire closed system is the fact that if we wanted to get the total number of moles in the system, it would be equal to the moles in the vapor phase plus the moles in the liquid phase. Now, since we are in a closed system, that means that pressure and temperature are going to be held constant. So further, we can say that the Gibbs energy per mole is going to equal 0. And thus, the differential in the moles is also going to be equal to 0. So now, taking all this into account, we can now look at an equation for the total Gibbs energy in our system. So what that would look like is something like this. No. And that's going to be equal to our total Gibbs energy per mole. I'm going to rewrite it like this. Now, if we were to take the differential of both sides of this equation, we would have to product rule this out. So let's go ahead and do that. So we would have dGV NV plus GV dNV, and we do the same thing for the other side. So dGL NL plus GL dNL, and that's going to be equal to the differential of NG. Now up here we stated that our differential of Gibbs energy per mole is going to be 0. So we can go ahead and cross that out. And by further conjecture, we could also go ahead, and since the pressure and temperature are constant, our Gibbs energy per mole here are going to be 0 as well. So these are zeroed out terms. So now what we are left with is GL times dNV plus, GV plus GL times dNL is equal to 0. Now up here, we also had we can also go ahead and using all of this, we could go ahead and say that the differential of the moles in the vapor phase is equal to the negative of the differential of the moles in the liquid phase. So if we go ahead and make that simplification down here, we get something that looks a little like this, where we have GV times the negative of dNL plus GL times dNL equals 0. So we could go ahead, if we go ahead and multiply that negative through and just move it to the other side, we get GL dNL is equal to GV dNL. And we can go ahead and cross out these differentials now. So if we just divide on both sides by the differential, we go ahead and we find out that the Gibbs free energy on both sides in equilibrium have to be equal to each other. Now, we can even take a little bit of a deeper look at this, and we can go ahead and write out the equations for each side. So that looks something like this, where we have a liquid component on this side, we have a gaseous component on this side. And when we take a look at this, we find out that what we're changing here is the entropy on both sides to keep our system in equilibrium. So that's how we're able to keep our Gibbs energy of the liquid and vapor phases in equilibrium to each other by go ahead and changing the entropy or the randomness of each phase. So now that we've covered that, we're going to go ahead, we're going to tackle our second part of this homework, which is to derive the Clausius-Clapeyron equation. So let me go ahead, I'm going to make some room over here. And we're going to start off with what we just found out. And whenever we look at the Clausius-Clapeyron equation, we are already assuming the fact that our Gibbs free energy in the vapor and liquid phases are equal to each other. That is the assumption we make when we look at this Clausius-Clapeyron curve. So first things first, we're going to go ahead and take the differential of each side. And now what we can end up doing is we could split these up into their equation components, right? So we would have our entropy of the vapor phase with respect to temperature and minus the specific volume in the vapor phase with respect to pressure. And we will go ahead, we'll do the same thing on the other side. So we have entropy of the liquid phase, dt, minus specific volume of the liquid phase times differential pressure. So now from here, what we can do is we can start grouping up on either side depending on what attribute we're looking at. So what's the best way to do this? So let's go ahead. We would have our SV minus SL dt is equal to I guess it would be the vapor phase minus the liquid phase here, dp. And so when we calculate dp over dt, we get SV minus SL over VV minus V sub L is equal to dP over dt. So now to derive the next part, we have to go ahead and we have to take a look at the enthalpy equation. So that is TdS plus VdP. Now remember that we had defined the change in our pressure as 0. So what we're really left with is dH and TdS. And if we were to solve for ds, we would get ds ds is equal to dH over T. And what this really means in terms of differential is that the change in our entropy is equal to the change in our enthalpy. So that's our enthalpy from one state to the another over T. Now, this top portion is what we call the delta H of vaporization. And so when we go ahead and we try and plug all this back into our original equation, we can look at this as our delta S. And so ultimately what we get, if I go down here, what we get here is delta H vap over T times specific volume of the vapor phase minus specific volume of the liquid phase is equal to dP dt. And so this is what we call the Clausius equation. But in order to get over to the Clausius-Clapeyron equation, we need to make the assumption that we are working with an ideal gas. And so with that assumption, let's move on with our derivation. Let's go on and get the last part of this derived out. So with our ideal gas law, we know that PV equals nRT, or T. And thus, if we wanted to go ahead and solve for T, we're going to assume 1 mole of it. We're going to assume 1 mole there. So what we have here, well, before that, let's talk about this right here. So we know that the density of a liquid compared to the density of a vapor when it's acting ideally is much smaller, orders of magnitude smaller. And thus we can kind of ignore the fact that we have this volume of the liquid phase just because the volume of the vapor phase is going to be so much greater than that. So we have delta H vap over T times specific volume is equal to dP over dt. And so what we're actually going to do here is we're going to solve for the volume of the vapor phase, which is going to be V equals RT over P. And so when we plug that in, we get P times delta H vap over RT squared equals dP over dt. And this is what we know as the Clausius-Clapeyron equation. And that's how we round out that derivation.